All right. Welcome back, everybody. Second talk for the afternoon session in here with Clinton Roy, who is an open source engineer at NetBox Blue, who organized PyCon AU in Brisbane in 2014 and 2015, and loves people. This is more testing with fewer tests. Please make him feel welcome.
So good afternoon, everyone. I am probably most well known to you folks as the organiser of last year's PyCon and the year before that up in Brisbane. It's very nice being able to give a talk and not also being the organiser of the conference. Ask Russell about that. So my talk today is on a lovely framework/library called Hypothesis. It's not my work. I'm probably the biggest fan of it, but I just want to make it really clear it is someone else's work, David McIver. I do give him full credit at the end, but I definitely wanted to make that clear up front. It is a lovely library for helping you automate some parts of your testing. We all know that we should do more testing, but writing test cases is laborious, it's repetitive, and because it's repetitive and boring, it's very easy to miss corner cases and regular cases that you need to be testing. Hypothesis can help with some of this. So we've got sort of three main parts of the talk. I'll quickly go over basic unit testing. I'll quickly go over property-based testing. So property-based testing is a language agnostic term for the style of testing that Hypothesis allows you to do. A really interesting feature that Hypothesis has is state-based testing. So it's a step further than property-based testing. And then I'll go into we probably won't have any time to go into details, but there's some really interesting stuff coming up in the further readings that I'll touch on at the end. So you've written a function, you need to test it. So you write a test case, you run the test, it passes or it fails, and then you do that again, and again, and again, and again, and again. So you want to spend your time writing the code that solves the problem or adds the feature, because that's the fun bit, that's the interesting bit. You don't want to spend time writing your test cases, because that's the boring bit. There are two sort of basic test cases that you're writing. You're writing your corner cases. So these are your people cases where your users put in weird, wacky things into your code that you would never think that they would, but they do because they're people, and people are really good at peopling. I've been at the registration desk all week, so there's the corner cases, the special cases that you have to check. And once you've done a fair bit of unit testing, you know off by heart what a lot of these corner cases are. So you're dealing with quantities, so you test the 0 case, the 1 case, the many case, and you might put in a -1 or something like that to test that. If you're dealing with strings, you've got a function that takes a string. So you'll put in the empty string, you'll put in a string with just white space, you'll put in a regular string with like 1 or 2 Unicode characters in it. Everyone knows these rules, they're not codified. So it means that when you're writing a test case to call these functions, every programmer on the planet, instead of automating something that could be automated, is basically learning these things over and over again and manually doing the same work over and over again. And I don't need to tell anyone, but that's silly. So just as a first example to get us started, a simple little function to generate the average of a list of integers. There is a fair bit of code in this talk. I don't want you to get too hung up on the code. It's just that I need to give some example so that we have some place to work from. So I've tried to make it as simple as possible. I've tried to use nice long variable names that are easy to read and understand that most of my workmates will probably shoot me for. So, just as a quick hands up, who can spot a problem with that code? And it might be something to do with like the length of the input string being 0. That's all good. Instead of us knowing about that, in really complicated code, like in this simple case, that's a pretty clear thing that's wrong with it. But in complicated code, it's not always obvious where the corner cases are. The corner case for some of your code, if it's accepting multiple arguments, it might be some weirdo combination of those arguments that you've never even thought of. So a very rough test case for this that you might handwrite is you call your function, you get the result back. The important point here is that we've handwritten the inputs to it, so the list of integers 1, 2, 3. We've hand worked out the output, which is 2. And then because floating point is fun, we've had to make sure that the result is roughly close to what we expect. And this is not a floating point talk, so I don't want any questions about the whole floating point absolute position thing. Just shutting that down right now. So property-based testing, you run the same test code 1,000 times, 10,000 times, 100,000 times. Hypothesis will generate different test inputs for each run. It will verify properties of the output against the input for you. So to make that a little bit more concrete, yeah, obviously you write the code. I didn't put that in the workflow here. That's a little bit obvious. You write your code. You write your properties. The properties map from your inputs to your outputs. Hypothesis generates the test data for you. You run your tests as normal. So Hypothesis has all the plugins and hooks so that you can run it with unit test, with PyTest, with nose, with whatever favourite Python unit test framework you're running at the moment. It will work with all of those. And of course, the other part of testing with all of these sort of tests, with unit tests or property tests, is that you look at your code coverage after you've run your tests, because it's going to show you those branches of code that you haven't tested. I'm not going to go into code coverage here. That's a whole separate talk. Hypothesis generates test cases for you. You still have to write the properties. So it's very possible that you are not going to write strong enough properties for your inputs and outputs mappings. You still need to think really carefully about your testing. And the thing that I sort of like about Hypothesis is that when you go into a unit test mode and you're just sitting there randomly generating inputs and outputs, your brain sort of goes into automatic and you stop thinking about things. Hypothesis, in a certain respect, is actually harder to write tests for because you've got to think really carefully about the mapping between your inputs and your outputs, the properties that define your code. It takes away the drudgery and the actual problem of describing all of your test cases is much, much harder than writing 100 individual unit tests. This doesn't take away from thinking. It doesn't make writing test cases easier in a certain respect. It makes writing them harder. So this is our first introduction to a hypothesis test. The import up the top for given. Given is the main API function to work with hypothesis. You use it mostly here as a decorator, and that's how it's mostly used. The other part of hypothesis that you'll be using all the time are the strategies. The strategies are the codified knowledge of all of the general cases and the special cases for all the data types. So for integers, for example, when you ask Hypothesis to generate test cases of integers, it will go through all of the usual corner cases. It'll do the 0, the 1, the -1, the 2, the 20, the 40,000. It's got all of the stuff that we know that we have to check, and instead of manually going through the corner cases and the general cases, it's got that codified. And the same thing with lists. It'll check, it'll generate a test case with an empty list, with one thing in it, with a few things in it, with a bucket load of things in it. So what we're asking Hypothesis to do here is generate a list of integers. And what will actually happen here is that decorator there will run the test average function. Depending on how you've configured Hypothesis, it could run it 100 times or 1,000 times. I'll come back to this a little bit later, but on your development laptop, it'll maybe generate like 1,000 test cases. On your continuous integration service that's running overnight, you can set a few flags on a Hypothesis and it will generate 1,000,000 test cases. So it will work within whatever workflow you're using. And it's very easy to set up those different modes. So we are calling our function. The property that I've chosen here to test is that the average sits between the minimum and maximum of our list. So I asked if there was a problem with the average code before, and Hypothesis finds it. So I've run PyTest, and this is like the bottom 10 lines of that because there's a lot of stuff. Right at the bottom, you'll see the actual example that it failed with. So the lists strategy generated an empty list, and the test function raised division by 0 error. So that is the style of output that you'll get with Hypothesis. It basically is sitting there generating all these test cases, running them, and if one of them fails, it'll let you know. And if anyone's got any questions at any point in time, just shoot up their hands. And I'll repeat because I don't like the microphone thing. So when you're generating test cases for real code, your code will have lots of limitations on the inputs that it can handle. And in this case, we wouldn't write a Hypothesis test to check for the empty list case. We would write a standard unit test to say, if you pass the empty list along, it'll raise some sort of value exception. So to get around this, we have to tell Hypothesis, generate me a bunch of lists of integers, but as you can see with the min size argument on line 6 there, all of the lists that you generate have to have at least one element. Now, I said this wasn't a floating point talk. I might have lied, because as soon as you use floating points, the corner cases are infinite. So this is the second run with Hypothesis. We've told it to generate lists of at least one element now. And what's happened here is that Python has cast our floating point number to an integer before it's done the assertions, because we've got an integer and it's trying to compare that to a float. It's done the cast, and if you have a look at the very last digit, you'll see that that cast hasn't quite gone the way we want it to. So the thing here is the reason that Hypothesis has chosen that extraordinarily large number is because it knows where the cast goes wrong. So there's a whole bunch of floating point cases where things get really funky. And Hypothesis, even though we weren't asking for floats, we were using ints because anytime you do maths code, you could be generating ints. One of the corner cases that Hypothesis uses is all of the integer values for the floating point values that Python has issues with. So it's just another codified form of all of the weird special cases that we don't even know about. Like the corner cases for floating point is a talk all on its own. So here we've just done the float call ourselves, which means that it's going to map properly. So the only change here is on our property, we've just done the float calls ourselves. And now we have no failures. So what does that mean? It means that for this run, all of the test cases that Hypothesis generated passed our property. So the problem here is that Hypothesis, because it's randomly generating some of these test cases, every time you run it, it will come up with different test cases. Now there are ways around that. So if you've got a bug report that comes in and there's a particular set of values that causes issues, you can specifically say, Hypothesis, this is an example and it's at example. This is a test case that I know fails and I want to test this every time because we fixed a particular bug about that. So you can do that easily. And also on your CI machines, you might want to generate tens of thousands of test cases. You can generate them once, save them, and then every night, instead of getting Hypothesis to generate new test cases, you can just get it to run the old test cases. So the other point here is that our property is pretty weak. We're not actually testing that our average is near what the average should be. We're just testing that our average is between the minimum and the maximum. So the point that I wanted to try and get across there is that it can be hard to write properties. You do have to have your thinking cap on. So Hypothesis generates tens of thousands of test cases if you let it, and this is a subset of the test cases that it's generated. So a minimum size of 1, it's got a couple of minus ones in there, it's got some very big numbers in there, it's got some very small numbers in there. That's just as a flavour. You can definitely run Hypothesis in verbose mode and see all the test cases, and it's very cool for about 5 minutes, and then you turn the verbose mode off. When you come across a failure, Hypothesis will store that on disk. So the very next time you run that failed test case will be the first one that it tries. So if you hit a failing test case, it will keep trying that one until it passes. So some other properties that are interesting to think about. If you sort a list of anything, the property between your inputs and your output is that the output is the sorted form of the input. You can have weaker properties, like the length of the input is the same as the length of the output, but obviously that's a fairly weak property because you could replace all of your apples with oranges and that property would still pass. And reverse is similar. You could, the appropriate property is that you can take your string, reverse it again, and you get your same output string. And it's a really interesting way to think about these test cases where you're not saying the specific inputs and outputs, you're just saying how the inputs and the outputs are linked. So everyone likes fax machines. So it's white and black. So you've got one line on a fax machine with whites and blacks. So you'll always have a lot of white and you'll have a couple of blacks. One of the simple ways of compressing it that is still used in JPEGs is run length compression. So if we had a single scan line and we compressed it, we would shrink the characters down like that. So very easy to understand from a diagram perspective. The code gets a little bit ugly, especially when you're trying to write all of it in such a way that you fit it all on one slide. I don't want you to get super into the code, but you loop over the characters If the previous character is the same, you just keep adding them up and printing out the number. And the decode is kind of similar. You just loop over the characters. If the previous one was a number, then you say the next one n times. So when you've got these pairing functions, so you've got an encode and a decode function, or a compress and an uncompress function, you've got two functions that do something to data, and then you've got another function that does the reverse. These functions are really good to use with hypothesis because the relationship between the input and the output, you can declare that with the code. So you zip a file, you unzip it, you should come back with exactly the same input and output. So what we've got here with the given text strategy, so there is a text strategy. There are strategies for all the Python data types. This one's a text strategy, and we've said only generate test cases with the letters W and B so that it matches my fax machine example. We take our input, we compress it, we decompress it, and we get the same result back. The other property I've got there is that so for an encode-decode function, the input and the output should be the same. For a compression function, I've got a further property there that the compressed form should be shorter than the uncompressed form, which, as we know, for some compression types, that doesn't actually work, but it is a property for run length encoding, fortunately. So there are many different ways you can think about properties. So you can do properties for optimization examples, for example, so that you can say, after I've run this optimization problem through n stages, it should be closer to the final goal. You don't have to say how close, you just say closer. So I run that, it's all good, there's no errors. One of the issues here though is that the random inputs that I'm generating with hypothesis are only getting passed to my encode function. They're not getting passed to my decode function. So I'm taking a random string, passing it to encode, and then passing that encoded string through to decode. So from a security point of view, this is not testing the decode side of things. So you do have to think carefully about all of these things. So these are some generated outputs. So a string with one W, a string with one B. There's an empty string there, and then there's a whole series where it has sped out multiple copies of W and B like we would expect to see on a scanner. So the really interesting part of hypothesis for me is the state-based testing. So instead of trying to generate test inputs and instead of trying to generate test inputs, we're actually trying to generate a program that fails. This is really good for testing data types. So you've got some sort of collection that you're adding, deleting, sorting, inserting to. You've got a bunch of operations where you're initializing your collection, you're adding a lot of results, you're taking a lot of results away from it. And those API calls could happen in all sorts of different interleaved ways. Hypothesis has a couple of really nice ways of doing state-based testing on this. There are a couple of spots so this is fairly new, there are a couple of spots of this API where it's a bit weak, and I'm hoping to add a couple of features to it. And I've sort of walked around those for this test because I didn't want to get into some of the uglier details. So it's a basic binary tree. All of the nodes on the left have to be smaller, and all of the nodes on the right have to be larger. So for the empty trees at the bottom, the squares, if we iterate over those, it's an empty list. If we insert into them, we turn the empty tree into a real tree. If we try to delete a value from those empty trees, we will raise a value error because there can't be any values in the empty tree. Fairly easy. For the nodes, we initialize them, and the left and the right, they're empty trees. We have a value. If we iterate over them, we get all of the left items, we get our cells, we get our right items. Fairly nice. The yield from them makes this really nice. Insertion is pretty easy. We just have to see if it goes in the left and goes down the right and then recurse down. And then we get the delete, and all of a sudden our simple binary tree gets a little bit ugly. And that nesting means that the test cases that we're going to have to hand write to test all of the corner cases for this is going to get really ugly. And this is a reasonably simple data structure, and it's already gotten quite complicated code. So I want to show some of the state-based stuff. I've had to split this up a little bit, but that will be fine. So we're importing our tree, which is the thing we're testing. We're importing our strategies, like always. The new stuff is the stateful stuff. So we're importing a few things from stateful. So we're making a machine. We're making a machine. It is a rule-based state machine, and we are subclassing that to make our particular test. We have our state. Our state is a bundle, and we're calling that trees. We have rules. The rules take an element of the state and do something to it. Sometimes they just do an assertion on that state. So this tree that I've generated, it's all in order. Other times, they're actually generating new state. So wherever we've got target equals trees, it means that the result of that rule is going to get taken and put back into the state machine. So it's a transition from one state to another state. So we've got our check down the bottom. It's a rule that will get run on all of the states, and it just checks that when we traverse the tree, we get back the sorted list, and it's in order. The top one, we take our, we basically make an empty node and we add that to the state. The middle one, we take one of our empty nodes, we insert a random number, and we make that into a real tree. So just with that, Hypothesis is going to generate random sets of trees. And because we're using the random numbers there, sometimes that tree will float all the way to the left, so all the numbers will be increasing. Other times they'll always be decreasing. Other times it will be nice and even and balanced. Other times it'll have like one little tree that's really long, and it will, over time, generate all of the different use cases that you want to be testing for without having to write any of them by hand. So this is the rule to test deletion. So it's another rule. It takes a tree. It takes a number, a random number. We've added the assume in there so that when we're generating random numbers, this test only makes sense if that random number we've chosen is actually in the tree. So that's what the assume is. And basically, if that assumption is incorrect, it will forget that that test happened. And it will delete that number from the tree and modify the state. So so we started off with quite complicated code for actually doing the fairly simple thing. The test cases for testing that, no branching, no looping, a simple state-based machine, and Hypothesis does all of the work for generating random trees for us and testing all of those weird use cases. So in this case, the code to do the testing is much, much nicer than the code that we're actually testing. Regularly, the test code that you're writing, where you're mocking out things, where you're working out weird input values and stuff, is quite ugly. In this case, it's not. One of the interesting test cases where you can treat something as a stateful machine is a code repository. Hypothesis has found a few bugs in Mercurial. You can treat a repository as a state machine. So you initialize your Mercurial repository, you make a branch name, and it was a strategy of text, and at some point in time, it's made a branch name with a double slash in it. You commit your change, you call a HG shelve, and it turns out there was an internal bug in Mercurial that if you did a shelve on a branch that had a double slash, a slash in the name, it would try to write that shelve information to a directory that didn't exist, because it would treat your branch name like a file path. No one would have ever thought to have tested this. Mercurial hypothesis came across this by random chance. So, hypothesis.works is the website. That is a real top-level domain. So David is a very interesting chap. The story about hypothesis, I recommend you go and read up about that. He's had some trials and tribulations. I don't really feel it's my place to talk about that. I think that's a fairly personal thing. There's lots of great documentation at hypothesis.works. He offers for paid training. I think he's being paid at the moment to try and port hypothesis back to other languages, because he's sort of struggling to get money out of the Python form, but enterprise people with Java will pay for tools like this because it means that they have to write less Java. And yeah, there's other integrations that I said we wouldn't get time to go into. There's special hooks for Django, numpy, and a few other things. And I did mention the settings. So thank you very much. We've now got some time for questions, I think. Oh, okay.
Thank you very much. Unfortunately, we don't have time for questions, so I'm sure Clinton will be available in the hall. And we'll see you back in 10 minutes for the next session.